Hello all, I am Tuğrul Yumak from Sinop University, Department of Chemistry, Sinop, Turkey. I'm gonna talk about a novel approach to synthesize biomass-based activated carbons for better capacitive performance in electrochemical double-layer capacitors. I wanna share our first results with you. I want to start with the energy storage mechanisms, electrode materials and activated carbon, advantages and disadvantages, then the hypothesis of our research, and after the experimental part, I will finish my talk with the conclusion part and future works. As you know, a supercapacitor, also called an ultracapacitor, is a high capacity capacitor with a capacitance volume much higher than other capacitors, but with lower voltage limits that bridge the gap between electrolytic capacitors and rechargeable batteries. Supercapacitors have far higher specific power, meaning they can provide a higher current compared to a battery. Therefore, it is obvious that the supercapacitors are used in such applications that requires instant high power, like hybrid vehicles, alarm systems, etc. Based on the energy storage mechanism, the supercapacitors can be classified into two groups: electrochemical double-layer capacitors and pseudocapacitors. In EDLCs, no electrochemical reaction takes place on the electrode, and the energy stored only by pure physical accumulation at the electrolyte interface. In the case of pseudocapacitors, the energy is stored directly by fast and reversible redox reactions. The thickness of the double layer is much smaller than that of the conventional separators. They have very high capacitive performance and higher power densities. In EDLCs, carbon-based materials are used as electrode materials, while metal oxides and conducting polymers are used in pseudocapacitors. Here you can see the requirements of a good carbon-based electrode material. It should have a large surface area and porosity, good surface wettability, high electrical conductivity, controlled or tailored microstructure morphology, and long cycle and thermodynamic stability. Biomass-based activated carbons with 3D networking structure, abundant mesopores, high macroporosity, and ideal pore size range are good candidates for electrode active material. What is activated carbon? As you know, it is a form of, it is a form of carbon with high surface area according to its pore characteristics. It can be synthesized from various carbon sources by direct or indirect activation, and you need maximum 900 C. You can use some chemical or physical agents like KOH, phosphoric acid, or CO2, and you obtain high surface area and pore volume. Here are some advantages and disadvantages of biomass-based activated carbons. For example, low cost synthesis in various forms, powder, fibers, composites, or monolites, ease of workability, relatively inert electrochemistry, controllable porosity are some of the advantages of activated carbons. However, we have some disadvantages. A biomass is composed of three different components: lignin, cellulose, and hemicellulose, and all of them have different thermal behaviors. And the poor energy storage capacity and inferior rate capability for energy storage applications. And when you want to synthesize a desired activated carbon for energy storage applications, we have some economical and environmental problems on the synthesis of activated carbon with the template approach. Uh, but we have the problem here. Uh, as I said before, the biomass is composed of mostly lignin, cellulose, and hemicellulose, and they have all different thermal characteristics. Lignin and hemicellulose are natural biopolymers, and they show classic polymer behavior with the increasing temperature. After the glass state, they turn into wax-like materials, and the wax state limits the formation of ordered porous carbon structure. Therefore, the softening of lignin and hemicellulose should be prevented. The glacis transition temperature, Tg, can be increased by controlling the heating rate. A novel approach, air stabilization technique, or we can call it thermostabilization, may fix this problem. Reactions occurring during the thermostabilization increase the Tg. As the temperature increases at slow heating rate, the Tg can increase faster than the temperature, maintaining the material in the glassy state, non-tacky or non-waxy. At higher heating rates, the thermostabilization reactions are not able to maintain the increasing of Tg, and the material the vitrifies entering the tacky liquid rubbery state, fusing together. Here are our research objectives. We tried to investigate the effects of thermal treatment or air stabilization prior to the chemical activation on the pore characteristics, the effect of direct chemical activation, KOH activation, on the surface area and porosity of the biomass-based activated carbon, and at last, the electrochemical properties of synthesized activated carbons. In our study, we select pine cone as a biomass source. And first, the pine cone samples were subjected to thermostabilization at 300 C at a heating rate of 0.1 C per minute in air environment. Then we chemically activated the resulting material with KOH. To see the effect of thermostabilization, pine cone samples were directly activated with KOH at the same conditions. And we marked the samples as SAPC and APC respectively, as you see in the slide. We conducted some electrochemical tests, cyclic voltammetry, galvanostatic charge discharge or constant current charge discharge, and impedance spectroscopy analysis. In this slide, we have nitrogen physisorption results. You see the absorption, desorption isotherms of the samples. The APC sample has a surface area of 830 meters square per gram, while SAPC sample has almost 1100 meters square per gram. And the total pore volume and micropore volume has increased in SAPC sample. The mesopore volume to macropore volume ratio has significantly decreased with the stabilization process. The BET surface area of the SA sample is almost 30% more than APC sample, and the micropore volume has increased almost 60%, as you see. When we check the cyclic voltammetry CV analysis, first of all, as you see, the shape of the CV curves are very similar to the commercial activated carbon, Norit A Supra, and the current in the SAPC sample increased as a result of the increased stored energy. You can see from the graphs, this is 2 milliamps, and in SAPC sample, we have almost 7 milliamps, as you see. In order to determine the specific capacitance, we conducted constant current charge discharge test. Then we calculated the specific capacitance in farads per gram. The specific capacitance in 100 milliamps per gram current density for APC sample is higher than SAPC sample. However, the Coulombic efficiency, which is very important to determine the workability of a cell, a supercapacitor, the Coulombic efficiency in 100 milliamps per gram is almost 35% and 65% for APC and SAPC sample respectively. Therefore, we worked at higher current densities, and it is found that the specific capacitance of SAPC sample is higher at current, is very high than APC sample, and it is almost 50% much more than. You can see at 250 milliamps per gram current density, the specific capacitance of SAPC sample is almost 104, and at this current density, the specific capacitance of APC sample is almost 90. To summarize the specific capacitance and see the equivalent serial resistance ESR values, the ESR value and specific capacitance versus current density were graphed. As expected, the specific capacity has decreased with the increasing current density, and the ESR value has increased with increasing current density due to the high current floating on the activated carbon surface. And we can say that the air stabilization technique led to lower ESR and higher specific capacitance at high current densities. In the EES spectra, in impedance spectroscopy, in the high frequency region, here gives two messages. First, the real axis intercept represent a combined resistance containing intrinsic resistance of electrode material, ionic resistance of electrolyte, and contact resistance between the electrode and the current collector. And the second, the radius of a semicircle is indicative of the electrode conductivity and the charge transfer resistance of electrode material, which is very important. In our experiments, it can be seen that the charge transfer resistance is lower, very low in SAPC sample compared to APC sample. In addition, the electrode conductivity, which is essential for high capacitive performance, is higher in SAPC sample. As a summary, the new approach that can be subjected to biomass with high lignin and hemicellulose content, thermostabilization, led to higher BET surface area and to development of microporosity, almost 60%. The specific capacitance has increased at higher current densities. The stored energy increased with the increasing current, and the thermostabilized sample in the thermostabilized sample, lower ESR and higher electrode conductivity were obtained compared to only activated carbon, chemical activated carbon, APC sample. We can say that the air stabilization is a successful and promising technique for activated carbon synthesis, and future works will focus on the application of the technique to other biomass types with high lignin and hemicellulose content. And we need to determine the surface chemistry in details, for example, and heteroatom containing groups, oxygen containing groups, maybe. And that's all for now. Thank you all for your attention. Please mail me for further questions and collaborations. At last, I would like to thank to TÜBİTAK, the Scientific and Technological Research Council of Turkey, for supporting our projects. Thank you again.